Alright, so guys, in last videos we talked about what was derivative, introduction to derivative, and the physical idea of the derivative. And we also discussed about the first principle of the derivative and the definition of derivatives and how we calculate the derivatives. But obviously the thing is that the process we have discussed to calculate the derivative of a function, it's pretty long and pretty hectic, right? And in the examples which I have given in the last video, they were definitely easier ones, and as we go up to more complex functions, things get more hard for us to calculate. So in this video we are going to try to reduce our hard work. So let's start off reducing our hard work with our notations. So let y equals to f of x. So f dash x be the derivative of f of x. It could be written as dy upon dx, where this dy upon dx means derivative of y with respect to x. Now in this video we are going to discuss some basic theorems, their proofs and their application, so that we can evaluate derivatives of functions easily. So let's start off with our first theorem, which says that derivative of function f of x equals to x to the power n is nx to the power n minus 1 for any positive integer. Now let's try to prove this theorem. Well, it's given that f of x equals to x to the power n. By definition, I can write f dash x as f of x plus h minus of f of x upon h, limit h approaches to 0. Let's put off the values into their right places. So I can write f of x as limit h approaches to 0, x plus h to the power n minus of x to the power n upon h. Let's give it this as equation number 1. Now, by using binomial theorem, I can write x plus h to the power n as this following expression. And if I subtract x to the power n from both sides, it will left as this. Now let's take h common from this expression, and I'm left with this expression, and let's mark this as equation number 2. So from equation 1 and 2, I can write derivative of my function as limit h approaches to 0, h, say a combination of n objects taken one at a time, and this following expression, and h just cancels out. It's just too hard for me to speak. So now let's put h approaches to 0. So here is my expression after cancelling after h and h cancels out each other, and now let's put h equals to 0. So here I am left with this, and which comes out to be combination of n objects taken one at a time, x to the power n minus 1. And for those who know what this c1n means, is it simply means n factorial upon 1 factorial upon n minus 1 factorial, and it could be n factorial could be written as n minus 1 factorial upon n minus 1 factorial, and n minus 1 factorial and n minus 1 factorial cancels out each other, and we are left with n x to the power n minus 1. So the derivative of the function is n x to the power n minus 1, and we have proved our result. Let's try out an example to understand it in a better way. Suppose f of x equals to x to the power 4, and I want to find the derivative of this function. Let's solve this problem. So let y equals to f of x, and so dy upon dx equals to the derivative of function, which is going to be d upon dx of x to the power 4. And by using this theorem, I can write it simply as 4x cubed, where 4 is the power which comes ahead of the x, and the power to the x is reduced by 1. That's how we have 4x cubed. Now let's talk about the algebra of derivatives. Now in algebra of derivatives, we are going to discuss some theorems whose proof I'm not going to discuss in this video because they could be simply proved by the first principle. And if you want to look at their proofs, you can use the internet, or you can just simply try them because they are simple. So the first rule says that sum of derivative of two functions could be written as d upon dx of f of x of plus minus of g of x could be written as d by dx of f of x plus minus of d by dx of g of x. So in simple words, if I say the derivative of sum of or difference of two functions could be written as simply the sum and difference of derivative of the two functions. I guess it's the same thing, but here it is written that what I mean. So let's try out a problem. Let y equals to x squared plus 5x, and I want to find out dy on dx. Let's solve this problem. So I have dy equals to x squared plus 5x, so I can write dy upon dx as d upon dx of x squared plus 5x. And let's use the theorem. So I can write it as d upon dx of x squared plus d upon dx of 5x. So the derivative of x squared is simply 2x, and derivative of 5x is simply 5. So here's my result. And now let's move to the next theorem. It says that derivative of product of two functions, also known as, this theorem is also known as product rule, could be written as like this, which is the d by dx of f of x into g of x could be written as f of x derivative of g of x plus g of x derivative of f of x, which is simply said as first function derivative of second function plus second function derivative of first function. Complex to speak, but easy to understand. So let's try out an example to build our understanding to a more better level. So here it's given as let y equals to x sine x. So I want to find out dy upon dx. So let's solve this problem. So I can write y equals to x sine x, and dy upon dx could be written as d upon dx of x sine x. And by product rule, I can write it as first function, that is x, derivative of second function, that is derivative of sine x, plus second function, that is sine x, derivative of first function, that is simply x. Now dy upon dx could be written as x cos x plus sine x, where cos x is the derivative of sine x and the derivative of x is simply 1. Now let's move to the next theorem, which is the derivative of quotient of two functions, also known as quotient rule, is given as like this. So this one is a bit harder to speak, but let me try it. So d upon dx of f of x upon g of x could be written as g of x derivative of f of x minus of f of x derivative of g of x upon g of x squared. So if I say it in a way as I said the product rule, it could be said as second function derivative of first function minus of first function derivative of second function upon second function squared. Again, hard to learn, but easy to understand. And let's try out a problem over this. So let y equals to x squared upon cos x. So I want to find out dy upon dx. So here is the solution to the problem. So dy upon dx could be written as, by using the product rule, second function, that is cos x, derivative of first function, that is x squared, minus of first function, that is x squared, derivative of second function, that is cos x, divided by cos x squared. Now it's going to be simply cos x, x squared derivative is 2x, minus of first function, that is x squared, and derivative of cos x is minus of sine of x. We haven't done this proof, but you can try this first principle to prove it, that the derivative of cos x is minus of sine of x. And again, the expression is divided by cos squared x. So simply dy upon dx equals to 2 cos x plus x squared sine x upon cos squared x. Now let's try out the next theorem, that is the derivative of a constant function. So is given as d upon dx of c equals to 0. So let's try out a problem to see what does to have a better understanding of this. So problem says let y equals to 5 upon x squared plus 1, and I want to find out dy upon dx. Let's see the solution. Dy upon dx by using the quotient rule is x squared plus 1, that is second function, derivative of first function, that is 5, minus of 5 d upon dx of second function, that is x squared plus 1, and divided by second function squared. Here the derivative of 5 is 0, so I can write it as x squared plus 1 into 0 minus of 5 into 2x divided by x squared plus 1, and which eventually turns out to be minus of 10x upon x squared plus 1's whole square. So let's move to the theorem number 5, which says that derivative of product of a constant and a function could be given as d upon dx of c of f of x, where c is a constant and f of x is a function. So I can take c out of the derivative and simply take the derivative of the f of x. Let's see an example. So problem says let y equals to 5x squared, and I want to calculate dy upon dx. Well, let's see the solution to the problem. So I have y equals to 5x squared, and I want to calculate dy upon dx. So it could be written as d upon dx of 5x squared. I can take 5 out and take the derivative of x squared, which is going to be 2x, and the answer is simply going to be 10x. So dy upon dx equals to 10x. Now let's meet our next tool, chain rule. Chain rule is a very important tool in case of derivatives, and we are going to learn this now. So suppose y equals to f of z of x. So I want to take derivative of y with respect to x. But now the thing is, in the questions or in the problem so far, we have seen that the function is the expression I want to calculate is a direct function of x. But now here f is not a function of x, it's a function of z of x. So how am I supposed to calculate the derivative of a function which is not a direct function of the x? Well, here is that the chain rules comes into place. So I can write it as df of z of x, derivative of f of z of x, and what I'm going to do is I'm going to take z of x as the base and going to take the derivative of f of z of x with respect to z of x, and then I'm going to multiply it with the derivative of z of x with respect to x, and this is what we call as the chain rule. Now let's see an example over this. Let's meet our last example, and in this example we are going to I'm going to try to actually sum up all the theorems we have learned so far and practice. So problem says let y equals to tan of x squared plus 5, and I want to calculate dy upon dx. And let's solve the problem. So I have y equal to tan of x squared plus 5. I want to calculate dy upon dx, which is going to be d upon dx of tan of x squared plus 5. Let x squared plus 5 be theta. So I can write d upon d theta of tan theta multiplied by d theta by dx. And we don't know the derivative of tan theta, so first of all let's find the derivative of tan theta, and after that put that expression into its place here and solve the rest of it. But first of all let's calculate the derivative of tan theta. So d by d theta of tan theta could be written as sin theta upon cos theta, and by using quotient rule I can write it as d upon d theta of tan theta equals to cos theta, that is second function, derivative of first function sine theta minus of sine theta derivative of second function upon second function square, that is cos square theta. So d upon d theta of tan theta, so derivative of sine theta is simply cos theta, and minus of sine theta, derivative of cos theta is minus of sine theta upon cos square theta. So d upon d theta of tan theta equals to cos square theta plus sine square theta upon cos square theta, and cos square theta plus sine square theta equals to 1. So what I'm left with is simply 1 upon cos square theta, which could be written as secant square theta. Now let's use this secant square theta in place of the expression. So d upon d theta of tan theta upon d theta upon dx, and let's put the derivative of tan theta as secant square theta. So dy upon dx equals to secant square theta d upon dx of x squared plus 5, because we put x squared plus 5 in we put theta in place of x squared plus 5. So it could be secant square x squared plus 5 d upon dx of x squared plus 5. So dy upon dx equals to 2x secant square x squared plus 5. So here is the derivative of the function we wanted to calculate. With this, I end my video, and thank you for watching this video.